How are you guys doing? Good to see everyone. Let me put, okay. Okay, welcome everyone. Let's get started. I encourage you, I have the a gallery view open, so I encourage you guys to turn on video if you want to kind of interact that way. It's totally up to you, but I think it's kind of more interactive for me to see how you guys are doing. But you can also interact with the yes and no buttons. Okay, cool. Hey guys. So today I'm just going to go over the any questions that you guys have from the homework. That's going to be the goal for today, kind of help you do any of the combination questions. Some of them later ones are a little bit tricky, so don't worry too much about like, I'll mention specifically a few of them that I think are a bit more challenging, but I hope that you will still spend some time thinking about them. And then today after class, I'm going to post a practice exam that once you complete the homework, it's the practice exam is only like 12 questions. I'll give you a sense of what I'm looking for on the actual test. And then I'm thinking that on Tuesday in class, maybe, let me think of how, so we'll do something that'll be kind of like an in-class, we'll do some sort of exam that's going to be take home and self-graded, but it might be, I might ask you to do it in class. And there might be, I'll think about how to do it, but prepare, yeah, I'll make it take home, but I'll try to make sure that you guys give yourself like a time limit to do it and then submit it by Thursday. That's my plan. And then I'll try to discuss with you guys on Thursday and see how you did and what was your overall, you know, where you feel you are in terms of the material and in terms of the class. Okay, so yeah, so today, those of you who just came in, we're going to just review any questions that you might have had on some of the concepts. We've pretty much covered all the concepts we need, so now it's just applying them and learning how to do these problems. So yeah, let me share my screen. Did you guys have any specific questions that you want to go over? And I made the homework, I think, due on the rest of the questions due on Tuesday, but if you can finish them by Monday or Sunday, it would be good. Yeah, 29 is that's a tough one. Oh, okay, yeah. If you haven't started the homework, you can still, still good to kind of review these questions and see how they're worked out, and then maybe like in 2 days, just try it without the notes. There's nothing wrong with that. Okay, question. And it can also be if you had questions about that we haven't gone over from 1 to 20 as well, that you're welcome to ask about that. So 29, 23, 20, 21, 22, and 25. Okay, nice, Angel. Okay, 24, good. All right. So let's go through these. This will give us a good amount of stuff to work on. Anything from 1 to 20? Any particular question that you guys had? Okay. And again, remember, it's not really about just kind of seeing the right answer and writing it down. You really want to make sure that you understand why everything works and how these questions are worked out. Let's do number 20. So if there are 3 cars and 4 motorcycles, how many ways to arrange them so that they alternate? Car and motorcycle. Okay, and 17 and 19. Okay, cool. So let me see who asked this one. Hannah. What did you think so far? What are some ideas that you had?
Would you add the 4 motorcycles and 3 cars so you would get 7, like in total?
That's right. Yeah, and there's something a little bit. Some of these problems you have to kind of interpret it, and always ask me if you're not sure. In this case, it's not like the ones with the yellow cars and red cars. In this case, I think you want to assume that the cars are distinguishable, like maybe they're different colors and the motorcycles are different brands or something. So it matters how you arrange them. But what's the only way to arrange 3 cars and 4 motorcycles so that they alternate in general?
Motorcycle, car, motorcycle, car, motorcycle, car, motorcycle.
Exactly. It has to be like this: motorcycle, car, motorcycle, car, motorcycle, car, motorcycle. And there's no other way to do it. But the thing is, like, if they're all indistinguishable, then the answer would just be 1. However, I assume the answer is not 1. That's not even a choice. So I assume what they're looking for is, well, you also have to decide how to arrange the cars. So there's 3 cars, so C1, C2, C3, and 4 motorcycles, M1, M2, M3, M4. So how many ways are there to arrange like in this kind of pattern? So once the pattern is already decided, how many ways do we have to pick out the arrangements of the cars? I'll get it close. You forgot one punctuation sign. So nice. There's 3 factorial ways to arrange the 3 cars. This is the number of ways to order the cars. And by the way, in all of these arrangements, they're always going to be motorcycle, car, and alternating. And then how about the number of ways to arrange the motorcycles? That's just going to be 4 factorial. Nice. And 3 factorial times 4 factorial. Archer, is that 6 times 6? Yeah, that's 144. Nice. Excellent. Okay. Hannah, is that okay? Did that awesome. Good. Okay. And yeah, ask me if you thought that if you're not clear if the objects are distinguishable or not or not indistinguishable, then just ask if you're not sure. Let's try. Let me see. It's 17 and 19. Ah, okay. So 17 is nice. How many ways can you choose one or more of 5 candies? Okay, so what do you guys think about this? So if you have 5 candies, let's say, Tootsie Roll, Gummy Bear, 5 different candies, how many ways are there to choose at one or more of them? Anyone have any thoughts or ideas? Oh, Angel, what do you mean by the pin problem? The one with what's your pin code?
Essentially, what I'm trying to say is that we have to figure out. Okay, so the way that I thought about this problem was this: we have 5 different candies to choose from, but we have 4 different numbers that we can put in for a pin code. But instead of having 10 different possible numbers for each one of those, we have 2, choosing the candy and not choosing the candy.
Oh, very good. Nice. That's excellent. So that's a really, really nice insight. Okay, so go on. Sorry. So we have our 5 candies. Candy 1, candy 2, candy 5. And so, Angel, what do we kind of, can you repeat what you said about each candy? What are we choosing?
You can either choose a candy or not choose the candy.
So this could be yes or no. So this is really, maybe I'll put it underneath it. This really means that there's 2 options, yes or no. And we have that for every single candy. And so overall, how many ways are there to pick some subset of these 5 candies?
Although I do want to clarify, it says 1 or more. So by minimum, we have to have at least 1 candy.
Yeah, good. So how do you account for that from this? Because this gives you 32.
Just subtract 1.
Exactly. And what does subtracting 1 do? Why do we subtract exactly 1?
We're subtracting the ability to choose whether or not we can choose the candy. By force, we have to have the candy.
Yeah. When there's one case, the case where you say no, 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 that case has no candies. So to subtract the case or the pin code, if you want to think of it, no, 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 no. So you get 32 minus 1 equals 31. Awesome. Angel, that's a really good insight. I like that. And so this kind of is a general fact that if you have 5 things, the number of subsets you can make, so I'll highlight it here. If you have, and think about kind of the argument that Angel made. It's a really nice argument. If you have n elements, the number of subsets is 2 to the n, because for each element you can just decide yes or no. Is it in my subset or not? Do I want to have it or no? So this includes also the empty set. This includes the empty set, and also the original set. And remember, a set is just a collection of objects, distinct objects. So does anyone see another way to do it? Because I think I talked to a few of you and we showed a different approach to doing this one.
I believe you could do 5 choose 1, 5 choose 2, plus 5 choose 2, plus 5 choose 3, plus 5 choose 4, plus 5 choose 5.
Nice. Yes, exactly. So an alternative way of looking at it is saying, oh, it's the number of subsets of, oh, sorry, not 5 choose 0. It's a number of ways I can pick a 1-element subset plus a number of 2-element subsets. So this is ways to pick, let me write it over here. This is ways, number of ways to pick 1 candy, 2 candies, plus 5 choose 3, plus 5 choose 4, plus 5 choose 5. And this is equal to 31. All of them, all 4 candies, and so forth. And so this builds to a really nice pattern. If you add in the ways to pick no candies, you get this awesome pattern. 5 choose 0, plus 5 choose 1, plus 5 choose 2, plus 5 choose 3, plus 5 choose 4, plus 5 choose 5, equals 2 to the 5th power. Okay. So this is a really nice pattern in Pascal's triangle. If you remember Pascal's triangle, the thing that we covered last week, and I introduced it, these are the numbers, the coefficients that you see in the expansion of x plus y to the n. So these numbers are 1 plus 5 plus 10 plus 10 plus 5 plus 1. And if you add them all together, you get 32. And if you do that for the next row, 6 choose 0 to 6 choose 6, you'll see you also get the next power. And the explanation is really nice. The fact is that there's 2 different ways of thinking about it. One of them is adding up these combinations, because obviously if you're talking about, if you want to count the number of ways to get a subset, you can kind of break it, each subset up by how many elements it has, and just count the number of those using combinations. Or alternatively, you can think about Angel's insight that, hey, for each candy, I have to actually, when I make a subset, I just have to decide I'm making a yes or no choice for each candy. So this is a really fundamental and nice fact about counting subsets, and a nice fact about Pascal's triangle. So this is a really nice pattern, that the sum of any row of Pascal's triangle is equal to 2 to the nth, where it's the nth row. What do you guys think? Does that pattern make sense? Please hit yes if it makes sense. Cool, or a thumbs up or something. Let's look up the practice. Oh, Gabby, yeah. So in this specific problem, we subtracted 1 because they said they talked about having at least 1 candy. So we don't have this guy. Because that's the case where we have no candies. Oops. My participants window. Oh. All clear, annotate. There we go. Okay. All right. Yeah, and I'll just kind of show you really quickly the triangle. Maybe I'll come back to it. 1. So just so that you really actually see it. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. If you look at the totals, this is 1, 2, 4, 8, and this is 16. So this is one of the really neat patterns. And later for the weekend, I'll give you another interesting pattern for you guys to think about. Okay, let's move on to, here I'll put the total. Let's try, so that was 17. So I really like that one. Oh, 19. So 19, Archer and anybody else who's curious about 19, I actually set that one up in the previous notes. So n choose 4 over n choose 2, nc4 over nc2. Recall that I don't use that notation too much. I'm going to write it like this, n choose 4 over n choose 2. And then I just kind of do what I did. What does n choose 4 mean? It means start with n, multiply by n minus 1, go 4 spots, n minus 1, n minus 2, n minus 3, and then 4, 3, 2, 1, divided by n minus 1, all over 2, 1. And this is equal to 1. So I'll let you think about kind of doing this carefully, but that's all. Is this setup okay? Did the setup here make sense?
An option as an answer though for 19.
Oh, what was that?
Number 1 isn't an answer available for 19.
Wait, in the notes I had the wrong answer?
No, I just meant that as a bit. Oh, that you were showing that one. Sorry, never mind.
Oh, my bad. Sorry. This is actually n minus 2. So I didn't read that properly. It's n minus 2. N minus 2, choose 2. So this is going to be n minus 2 all over n minus 1 all over 2 times 1. And I'm going to put parentheses here because it's like, this is a fraction divided by another fraction. No, that's not, my bad. What am I doing? N minus 3. You're counting down by 1. So any questions on this setup? So I go through the same thing in the notes. One thing I would remember is that when you divide a fraction by another fraction, you have to remember to multiply by the reciprocal. So multiply by the reciprocal, you'll see nice things will cancel. These n minus 2s and n minus 3 will cancel with these when you multiply it all out. So these will all be gone. And you'll just get left with the algebraic expression, clear the denominator, move it to one side, and you'll have a quadratic equation that you can solve. So please look it over in the notes. If you need any help with that one later, just let me know. But yeah, the key is just setting up, like understanding what this means abstractly, because it's not just a number choose for, it's n choose for, and how to write this down once you have to deal with that, and then carefully writing this as well. And as you saw, I made a mistake also, but just be careful setting it up. And I know the the algebra looks a little bit intimidating, but try it out on your own and compare it to what's in the notes. Okay, let's try number, so we did 19. Let me see. So basically 21, 22, 23. Okay, and 24. Are we doing all of them? Yeah. Okay. And I'll try to get you guys involved. So please, if you know how to do one, it would be awesome to hear your ideas. So let's see, 21. There are 9 people participating in a raffle, and three $50 gift cards from the same store are to be given out as prizes. How many ways can the gift cards be awarded? What do you guys think for 21?
Nine choose 3 probably.
Yeah, that's what it looks like. Anyone check that? Does that work out? 9 choose 3? That's what it seems like. I don't think this one is anything. Okay, yeah, excellent. Yeah, so this is just 9 choose 3, and just a simple combination like this, I expect you to be able to do without your calculator. So 9 times 8 times 7 all over 3, 2, 1. These cancel, leaving you with a 3. This leaves you with a 4. So it'll be 12 times 7. And that's going to be 12 times 7 will be 84. Okay, number 22. So a set of tile contains 8 letters. If 2 of these are combined, how many ways can all tiles be arranged? So we have A, B, C, D, E, F, G, and H. And I'm just writing it out. Obviously, when you solve this in the future or something similar, you don't have to write it all out. And then I'm have another set of like Scrabble letters, another one, A, B, C, D, E, F, G, H. So what do you guys think? How many ways are there to rearrange the whole thing? And what problem is this essentially identical to, just with different numbers? And message me also in chat if you don't want to. So what do you think? Who knows? If you know, so please message me this one if you know exactly what problem this is like or what concept this is, or if you're totally stuck also, just so I know where people are at. Nice, Angel. Yeah, and everyone else, nice, Aiden, very good. Adam, excellent. Message me if you're not sure at all what the idea is. Neda, very good. Okay, cool. We got a few students who are confused. Excellent. We got 4 students who are not sure what this is like. Good. So those students that are a little bit confused here, what do we know about rearranging letters? Do you guys remember, like, if I just have 16 letters and I want to just rearrange them? Oh, okay, thanks, Mason. If I have 16 letters and I just want to jumble them up, what tool do we have to just jumble up letters? Isaiah, very close. Yeah, maybe anybody who I called out who said that, like either Adam, Aiden, Neda, do any of you guys want to volunteer to kind of explain, or Angel?
Well, we have 16 letters, but
Mhm.
if we want unique combinations, we'll have to account for the fact that there are 2 of every single letter.
Nice.
So you'd have to divide by 2 factorial 8 times, which you can simplify that to 2 factorial to the power of 8.
Exactly. Thank you, Neda. Very good. And what is this problem essentially the same as? What was the name of that problem? This is the same idea as nice. Exactly. Nice. Nice, Archer. Yes. Yeah. Yeah. Sorry, your internet went down. Mississippi problem. The same exact idea, except in this case, like Nanda pointed out, we have the repeats show up twice, and there's 8 different letters that are repeating exactly 2 times. So that's why we have 2 factorial 8 different times. Those of you who were not sure at first, those of you who messaged me that said you didn't have any idea or you're a little bit confused, is it clear now? Is it? Awesome. Okay, the 8. Excellent. Okay, good question. Okay, so the 8 comes from the fact that we have yeah. So there's 8 letters here. A, B, C, D. There's 8 letters. So another way to rewrite it is like this: A, B, B, C, C, D, D, H, H. So there's 8 groups of 2. So that's why I'm just doing 2 factorial, 2 factorial, 2 factorial for each pair of letters. Awesome, good. And I'm going to ask a similar one like this on the test. So, okay. 23, I really like 23. I'm curious if anyone had thought about it, and I think I might have gone over it in the notes, but this is one of the awesome applications of combinations is path counting. So you can, for number 23, it says you can only move south and east. So here's A, here's B, and then it's a 3 by 3, so you can go this way. And I'm just drawing it out here. 1, 2, 3, 1, 2, 3. Okay. Archer, how did you get it?
I separated it between all the combinations you can do from A to B and then from B to C, and then
Oh,
I
yeah.
moved the possibilities together, and I got 120.
Yeah, that's wonderful. Why did it feel wrong the way you got it? That's a really good way to do it.
Because I kept thinking I had to add the 2 different combinations together. Well,
Uh-huh.
the 2 different possibilities together, when in
Right.
truth, all I do is multiply it.
Exactly. Do you see why it's just why you need to multiply? Oh.
Not really still, but it worked.
Yeah. So let's talk a little bit about it first. So Archer had this idea which is that to count the number of ways, by the way, we can only go to the right, east, and down, which is south. So we're only allowed to make these types of paths. Now, Archer says the number of ways to get from A to C is first the number of ways to get to A to B times the number of ways to get from B to C. Does that make sense? What do you guys think? Why is that a reasonable thing to say? Why do we want to multiply the number of ways and not add them?
Maybe because we're not thinking about like the individual ways to get from A to B and then B to C. We're thinking about how to get from A to C directly.
Mm-hmm. Exactly. It's this idea. It's like Billy's outfit, right? Billy first has to pick his shirt, and then he has to pick his pants. And the number of ways is he has a certain number of shirts and has a certain number of pants. And then to figure out the total number of outfits, you multiply. Because for each shirt, he can pick a different pant, right? So it's the same. It branches out exactly. So for each way you pick from get to A to B, then you're at B, and let's just say for example you had 20 different ways to get from A to B. So each of those 20 ways, you're going to have the same number of options to go from B to C. Exactly. So one thing that I always kind of have in my mind is, and this is a common difficulty with these problems, is when do you multiply, when do you add it? And I don't encourage any sort of memorization of like, just make sure you really understand the concept. But one thing that that I keep in mind is when I'm trying to talk about an entire path or an entire configuration or an entire outfit, and I have options for each part of it, I'm multiplying. But if I have like different cases of entire outfits or entire paths, then I'm allowed to add or subtract if I want to exclude certain things or include other special cases. But if I'm just building it out from start to finish, I would multiply all the different options. Okay, so what is the insight to? So that's kind of the main idea, that we're going to multiply the paths from A to B and then B to C. How did you count the paths from A to B? Archer, did you have any way of using combinations or any way of thinking about the paths from A to B?
Well, for A to B, I also thought I think it was the study session on Sunday where we talked about like it was when we were doing the binomial stuff.
Uh-huh.
And there was the because that one was the 5 digits, I think, and it was the not 5 digits, but basically how each bit is like half and half. That's how all of them have to be. It always has to be half. So then I just did the 4/2, which is equal to 6. And then for B to C, it's 3 different east, 3 different south.
Yes.
And then it was 20. So then I multiplied 6 times 20 and got 120.
Nice. So very, very good. Awesome, Archer. I'm glad that you connected it. So this is one of my favorite things about this topic, is that all these different ideas, you can connect a lot of them to just writing down words with different letters. So kind of just for example, we just saw with Angel's solution for that one with the candies, you can say for each subset, it really corresponds to like a pin code of yeses and nos, YN, YN, and then we counted how many of those you can make. A path here, for example, this green path, if we wanted to actually write it down and call somebody up and say, how did you travel, not draw a picture, but represent it as a word, you can say east, south, south, east. And the red one would be south, east, east, south, east, south. So there's a connection between the ways you can draw the path and writing out, well, no matter how you draw the path, the key observation is that you're going to have to go 2 steps to the right and 2 steps down. There's no way to avoid that. So you're always going to make a total of 4 steps from A to B, and 2 of them are going to be to the right and 2 of them are going to be from the left. Sorry, 2 of them are going to be down. So overall, we know that there's 4 choose 2 different ways to pick the 2 spots to be south, for example. And then there's 6 choose 3 different ways to pick, let's say, where you want to put your south, the S's for the B to C. And then you calculate this. This would be 4 choose 2 is going to be 4 times 3 over 2 times 1 times 6 times 5 times 4 all over 3, 2, 1. So I'm just going to simplify. The 6, 3, 2 is gone. So just 20. And then this is gone here. This is just going to be a 2. So it's going to be 6 times 20, which is going to be 120. Okay. Any questions? Angel, yes, 6 choose 3 because there are 6 letters for the B to C. You have to make overall 6 kind of moves. You need to make 3 down moves and 3 right moves. There's no way to avoid that. So you just have to pick where are the 3 down moves, for example. That's why you do 6. Choose 3 of the spots to be down. The other 3 spots will automatically be going to the right or east. Any questions? What do you guys think? Did that idea make sense of path counting using combinations? Angel, is that okay with why it's 6 choose 3? Okay, awesome, cool. Yeah, any other questions? Please hit yes if that if 23 is crystal clear to you now. Now the idea makes a lot of sense. And no if you're still a little bit confused with what we did there. Because I really want to make sure that you're on the same page. Yeah, why do we do 6 choose 3? Because yeah, so here 6 choose 3 is because you're going to need to make, to get from B to C, you have to go 3 steps to the right and 3 steps down. So 3 steps to the right and 3 steps down, you're going to have to make overall 6 moves. And 3 of those have to be down steps and 3 of them have to be east steps. So basically you have 6 moves. You got to choose 3 of them to be going to the south or going down. Yeah, so for the arithmetic, I just do 4, 3, 2, 1. The 2's cancel here. This leaves me with a 2. So that would be an overall 6. So 4 choose 2 is just 6. And then 6 choose 3. The 3 and the 2 cancel with a 6, leaving me with just 20. And that's how I got 120. Let me see here. And I'm happy you guys are asking questions. Very good. I see where the 4 came from, but why is it choose 2? Yes, so we have for A to B, it's 4 choose 2 because you have to take 2 steps to the right and 2 steps down. So you're overall got to take 4 steps. And then you just have to, the different paths consist of choosing which 2 steps are down and which 2 steps are to the right. And so if you look at that, that's really going to be just 4 choose 2. Yes, in combinations, you will get a lot of cancellation. So I recommend when you calculate combinations, you do simplification and then multiply through. Yes, Hannah, that's a great question. So this is the thing with combinations, right? Uh, uh, when you have a, a six-letter word where three of them have to be, let's say, E, and the other three have to be S, one way to think of 6 choose 3 is pick the 3 spots to be E, and then the other ones are automatically S. Another way to think about it is pick the 3 spots to be S, then the other ones have to automatically be E. But as long as you know it's going to be either one or the other, you can just focus on picking one of them. Just to kind of do a really quick warm-up or a little kind of review here. What if we had a 3 by 4 rectangle? So 1, 2, 3, and then we had these. And we can only go, let's say, I'm just going to, rather than east or south, let's just say down and right. So what do you guys think? How many different paths are there to get from the top left corner, A, to B? What combination would that be? And just message me in the chat what combination is it, and it's good to practice as well. So now I have a rectangle. It's not a square, but it's a rectangle. How do I count the number of paths from A to B? And I'm only allowed to go to the right and down. Nice, Gabby, very good. Bill, going to be a little bit more, be careful. You know, in the chat, you can, if you want to write a combination, use the C. It's actually pretty good. It is good in the chat to do that. So Diana, I think you're right, but I don't think you mean that exactly. Nice, Hannah, very good. And Hannah, do you see you can also do it with the other way? If you want it, rather than counting the down letters, you can also do the other combination, counting the right letters. Awesome, nice, excellent. So I got a few answers here. 7 choose 4, or equivalently 7 choose 3. They're the same. Just picking, if you have 7 letters, this path, for example, is going to be right, right, down, right, down, down, right. So there's 7 letters. It's really like the Mississippi problem, but I like to think of it as combinations. 7 letters, pick either 3 of them to be D's and the rest R's, or pick 4 of them to be R's and the rest D's. Either way is correct. And then it's always easier to calculate the one with a lower number of things you're picking. So it would be 7, I would do 765 over 3, 2, 1. These cancel. This leaves you with 35. Excellent. Okay. So that's one really cool a way of thinking about combinations. And I'll show you a really neat pattern. It also is secretly, actually, there's Pascal's triangle is secretly inside of this concept as well, which is not super surprising because Pascal's triangle is made up of combinations. Okay, let's try number 24. Wait, was that one asked? 24, 25. Okay, good. Yeah, I think we can finish these two. So number 24, a bookshelf has n fiction books and 6 nonfiction books. So n fiction and 6 nonfiction. There are 150 ways to choose 2 books of each type. So 150 ways to choose 2 books. How many fiction books?
Wait, so for this one, do we kind of go like backwards?
Yes, exactly. That's right. We don't know the total number, but we know something related to the combination. And Angel wrote exactly the formula. So there's 150 ways to choose 2 of each type. So that means n choose 2's number of ways to pick 2 fictions times the number of ways to pick the nonfiction. So 6 choose 2. And then you can solve from here. 6 choose 2 is going to be 6 times 5 over 2 times 1, so that's 15. So you get that 150 equals n choose 2 times 15. And then this cancels, leaving you with 10 is equal to n choose 2. And you can, if you wanted to, you could solve this, write it out. You could write n times n minus 1 all over 2 times 1, multiplied across. So this is a strategy. If you can't, you don't need to do it this way if you see the answer, but this is how you could do it if you don't see the answer. You can expand, then write equal to 0. You get n squared minus n minus 20. And then this can be factored. This is from algebra. You can do n minus 5 times n plus 4. And of course, this implies that, because n has to be positive, this implies that n equals 5. Any questions on that one? Why did it become 20? Oh, I just cross multiplied. This is 10, and then it's n over n minus 1, and there's a 2 in the denominator. So that's how I just multiplied. I cleared the denominator. All right, so let's try number 25. Number 25 is a good one. It's not really like, there's nothing too complicated, like there's nothing too deep about it, but it's nice to practice the fundamental counting principle. So 5 courses are required. So I'm going to just do it here. Math, science, English, or other. And we have Math 1, Math 2. Then we have biochemistry, physics. We have an English class, and we have option A, B, C, D, E. So this is the things you can make. And you have to take either math or math 30. You have to take 1 math class, an English class, and at least 1 science course. How many ways are there to pick 5 courses on the application? So I really like this problem just because it's good practice on how to be careful with these sort of casework problems. And I really encourage you, if you haven't done any of these questions yet for homework, do them on your own, thinking, like, read them over and just see if you can set them up like tomorrow or after tomorrow, just on your own without the notes, especially this one. So how many ways to pick 5 courses? So what do you guys think? What ideas will we have to use here? And what simplifications can we make?
Thinking out loud, we could probably do something choose 5 minus the ones that are mandatory.
Something choose 5 minus the ones. So that's a good idea. because you got to pick 5 of the courses, but it's tricky because there's some sort of like yeah, because dealing with the mandatory ones kind of means it's actually it's a good idea. Uh, uh, you'd kind of just want to do even because you need to pick one of the math courses and English courses. You really only have to choose 3 from some of the, from some of the options, but you need to have at least one science as well. So I would encourage this to do this one is by cases. So there's different cases that kind of, if you look at different cases, sometimes you can just do the fundamental counting principle pretty easily. So there's different cases. So case 1 is if you pick one science course. Well, how many options are there for the math course? For the science course, the English, and then the other course. What do you guys think? How many options are there for math? Always 2. How about for science, if you can only pick one science course? There's 3. Excellent. And how about English? Well, there's only one English course. You always got to take that English course. There's 1. Okay, now keep in mind, we got to pick 5 total, and we've already picked a few courses. So no matter what, if you only pick exactly one science course, the others will be, that's right, Gabby, nice, exactly 2 other courses. Okay, and then you just multiply those, and that will be the number of ways you can pick exactly one science, have a 5-course schedule that meets the requirements, but has exactly one science course. So what is that? That's going to be 2 times 3 times 2 is going to be 12. How about 2 science courses? What do we have to change?
Put 2 slots for science class?
That's right. In particular, I'm going to write 3 choose. Oh, 2 science courses. Actually, it's going to be oh, see, you said put 2 slots. You know what? So you can sometimes use combinations to just think about this. So I'm going to put 3 choose 2, which is also 3, but that would account for the number of ways I can pick a pair of science courses, which in other words is another way of saying this, pick the course that you don't want to take, and then you're going to automatically enroll in that one. And then once I do that, how many other courses can I take? Oh, hang on. Wait a second. How many other courses? Hang on. Option A. This is a mistake here. This is not. It's 3, 1, and then this last number is. Sorry about this. This has to be. There's two of them, so there's 2 different ways. 5 choose 2 over here. Yeah, sorry about that. So once I have 2 courses left over, the last one will be 5 choose 2. So this will be 6 times 10, which is equal to 60. The last one here is 6 choose, not 6, 5 choose 5 choose 1, because I already picked 2 science, 1 math, and 1 English. So now I'm picking exactly one of them, 1 out of the 5. So there's 5 options there. So that would be, again, 2, 3, 1, but this time times 5. So this would be 6 times 5, which is 30. And the last one is when they're all science, 3 science. Well, I can pick 2 math, but there's only one way to pick all the science courses, which is really 3 choose 3, just 1. The English course is always determined, And now the other courses, there's only one way to pick none of them. I got to pick no courses there. So this will just be 2. And then grouping them all together is going to be 92. Okay. All right. Any questions on these exercises? We didn't get to do too much with binomial theorem, but I will post some more practice that we can discuss in class on Tuesday. And then after class Tuesday, I will give you guys a take-home kind of quiz that's important to do because it'll determine kind of if how you feel about the class and if will be able to keep up. Why is 1 science 5 choose 2? Okay, very good, Fiona. So it's 5 choose 2 because if I pick 1 science, then I picked 1 math, 1 science, 1 English. So I picked 3 courses. I have 2 empty spots available for taking another course. So I can take option A, B, C, D, or E. So out of the 5 options, I can need to only choose 2 of them that I can take. And I can pick any of the 2 that I want. So that's why for the other courses, it's actually, there's 10 ways to pick 2, extracurricular or whatever other courses, which is 5 choose 2. Fiona, is that okay? Awesome. Okay, guys, and I'll be around a little bit after 4 if you have any other questions as well. But otherwise, and you're welcome to stick around, but I'm going to start the next class. So I'll see you. Have a wonderful weekend and see you guys next time.
Thank you.
Bye.
Have
Thank
a
you. Have a great weekend.
You too. Bye.
Thank you for your help.
Bye. Thank you.
You're welcome. See you guys. Bye. Hello. Hey, Lily.
Hello.
Okay. So today I was just going to go over any homework questions that you guys had. So hopefully we'll be able to get through a bunch of those. And then I'm going to post over the weekend some practice problems, maybe like I'll post it today or tomorrow. And then we can also discuss the practice problems will be kind of similar to like an exam or quiz. And then we'll go over all of that on Tuesday. And then my plan is to give you guys, the homework. The homework, it's not due yet, but the rest of the questions, just kind of anything past the rest of the packet. And then, yeah, so try to kind of look over the practice questions I send out and the homework, making sure you understand those concepts. This way on Tuesday, if you have, when I give you guys, like, I'll give you a take-home test essentially, and we can go over that on Thursday. And really the point of the take-home test, it's, I'll grade it like a quiz, but it's mostly just to see if you're able to keep up with the class. And then maybe the week after we'll have actual in-class or something that will count as an exam. All right. Did you guys have any questions that you wanted to go over from the packet? I know you might not have gone to see all of them, but that's okay if you see one that you haven't had a chance to work on yet. Please, like in a day or two, still do it. And make sure you remember kind of what we went over and stuff like that. Okay, yeah, so Lily, 23, 25. Yeah, just feel free to write down, message me any ones that you want to go over. So 23, and also anything from earlier, from 1 to 20, I'm happy to discuss those. 2931 what's an expansion one? 25, 25, 40, and 35. Okay, let's try to do these. 34 and 36. Okay, so maybe 34 or 36. Okay, let's see how many of these we can get through. All right. Kai, number 9. Yeah. Okay. Oh, number 9. Yeah. So number 9. Yeah. Let me go over number 9 first. I think I might have mentioned a little bit previously in one of the notes. Number 9 is a kind of a tricky one. The observation is that A, or let's say N P K, if it's just a random K, this means start off with N, go down N minus 1, N minus 2, dot, 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 until you go all the way down to N minus, so this is kind of weird. You're going to do N minus K plus 1. And the thing is, you just go down K steps. So this is K spaces. You can, yeah, you would say not 2p3, but 3p2. You would say that's a good question. Maybe 3 permutation 2 or 3p2. I don't know exactly. I would have to look that up. But using permutation, like 3 permutation 2 would be okay. But there's another way of writing this that's useful. It's kind of like n factorial, right? So the numerator is sort of like n factorial, but we're stopping until we have k spaces. So what that tells us is you want to divide out the smaller factorial, n minus k. So just to give you an example, 10p8, so 10p3, well, we know that this is going to be 10 times 9 times 8. But a nice way to do it is to say, oh, this is 10 factorial, but just get rid of the first 7 factorials. That would leave you with the 10, 9, and 8. Kai, so far so good?
I think, yeah.
So this is a convenient way, abstract but convenient formula for NPK. So this way, because it's pretty easy to do like NP3 or 10P3, but when it gets a little bit tricky, like in this problem, it's nice to know this idea that, oh, it's to only get the first leading, the biggest numbers of the factorial, I can actually take the entire factorial and divide out by a smaller factorial, n minus k. So n minus 1 p n minus 3, well, that's the numerator, or the expression is kind of like n minus 1 factorial, but the problem is in the denominator, or it's not going to be a full n minus 1 factorial. It essentially goes almost all the way. The number on the right of the p tells you how far down to go. It doesn't go quite all the way. It actually is just too short of the end. So what you're really just missing from n minus 1 factorial is a 2 and 1. So I'll put it in the formula, but I don't mean to, like, I'll put it in the full formula. you don't actually need to do it this way, but this kind of just to justify it. This is going to be n minus 1 factorial divided by 2 factorial. Essentially, the way to interpret this is it's essentially like n minus 1 factorial because this number is so big compared to n minus 1. It's almost the same. The only thing is that it doesn't go quite all the way down to the end. It just misses out on 2 and 1. That's why we divide by 2 factorial. Okay, once we know that, then we just plug into the formula, into the equation they give us. N factorial over 10 is equal to n minus 1 factorial all over 2 factorial. And let me actually, hang on. Oh, excellent. Yeah, so this is, now you can write this as, I'm going to put an arrow here, the new equation, cross multiply, I get n factorial over n minus 1 factorial is equal to 10 over 2 factorial, but that's just 2. So this is just n, because n factorial over n minus 1 factorial is just n, is equal to 5. Okay.
Wait, so you cross multiply?
Yeah, just cross multiplied, simplified the factorials, and that's it.
So we would get the bottom number for permutations by how? So for the 10 permutation 3, we get the 7 because it's 10 minus 3?
That's right, that's right. So 10p3, right? It means start off with 10 and then count, just multiply from 10 going 3 steps down. An alternative way of thinking about that is like, well, don't go all the way down, take away the first, the smallest 7 numbers. So that's 10 factorial over 7 factorial.
Okay, thank you.
Mm-hmm. So for n minus 1 p n minus 3, and this is kind of where it gets a little bit weird, right? You're saying, oh, start off with n minus 1, but don't go down all the way. Just stop too short of the end, because n minus 3 is 2 less than n minus 1. So that's why I'm just dividing by 2 factorial. Okay, very good. That's a good question. That one's a bit more challenging. If anything, if I had one like that, maybe it would be extra credit. All right, let's try number 23. I really like 23. Yeah, maybe on Tuesday, maybe today I'll mention why also. So yeah, this one here. We have a picture like this. We have 2 squares. And there's a really nice insight. It's one of my favorite problems because it shows all the different ways that we can interpret things and actually see them as combinations and stuff like that. Okay, anyone have any ideas? Want to share their approach for this one? So, and you can only move right and down. Here they say southeast. I'm just going to say right down. How many paths? How many paths from A to C? What do you guys think? Anyone solve this one? Anyone have any thoughts? Yeah, Dimitri, how did you count it out? What did you do?
Okay, well, starting at A, you have 2 different directions. So you pick one, or so you count 2 directions.
Mhm.
Then you're adding 2 more for each of those, and then you add 2 more for each of those, and then more for each of those, and you just keep counting And then since it converges to B, you can just count those, write it down, and then keep going from there. But if you really wanted, you could keep doing it.
Yeah, so can you walk us through that? That's I think I know the approach that you're talking about. So yeah, what are you doing there?
It's like when you make those the trees, the probability trees. You have two directions, and then each of those directions has two directions, and each of those directions two directions.
True. That I agree with that. But sometimes you don't have a like if you
It
end up
changes
in
it
the
a little
corner.
bit because you can't go up, so it changes it a little bit. But
Right.
if you since it's so simple and symmetrical, you can just follow all the different paths.
Okay, so how do we do that?
Oh, okay. So left and right, that's 2. Each of those has 2, so that's 4. And then each of those has, well, and then there's 1, 2, 3, 4 left because there's 4 different ways to move on. And there's 2 different ways to move on. So you add all that up, that gets you to 12. And then from B, you can go either left or right. So that's 2 different options. And then there's 1, 2, 3, 4 more options from there. 1, 2, 3, 4, 5, 6 more options. 7, 8, 9, 10, 11, 12 more options. Or actually, I lost count there. But there's 24 more options in B. There's probably some relationship between the width and the number of options, but you can just count it out.
Yeah, so
I noticed that the B is twice as big as A. I don't know why.
yeah, so there's I like that idea. There's something a little bit you have to be careful with, like so you're right that there's there's 2 different ways you can go from A. So you can end up here and here, and then there's 2 different ways you can go from A to get to one of these dots. But then it gets a little bit tricky because there's only some of them only have one way, and I know you were kind of referencing this. You can only go, the middle one can go 2 ways, but the ones that went the other ways can't quite go. But there's another way, and this approach is actually connected to a really nice pattern. But there's another kind of even simpler way to see it. And that ties in with something that we have done. So first, let's just focus on this idea. Do you guys agree that, if I just going to draw a path here, purple, so a number of paths A to B. So if I can count that times, let's say, the number of paths from B to C, then I will multiply those 2. So are you guys okay with that idea that the number of overall ways to get from A to C is I have to figure out how to get from A to B and then multiply how many ways there are to get from B to C. Now, does anyone see anything that every path will have in common? So any path from A to B, what do you always have to do?
Either go down 2 and right 2.
Exactly. So you always have to total make 4 moves. 2 of them have to be right, and 2 of them have to be down. What tool do we have to calculate that? What is that really similar to? I can express this as right, down, down, right. Nice, Lily, exactly. It's just 4 choose 2. I got to pick my 2 spots in my journey that are going to be going to the right. The other ones are automatically going down. So that's 4 choose 2. And then how about for the red one? Based on that logic, what combination would the red one be?
6, choose 3.
Nice guy, exactly. That would just be 6, choose 3. And it's a really beautiful idea that if you're restricted to moving only only right or down, then you can calculate paths from 2 points on a grid by using combinations, because it's really, for this one, it would be down, right, down, right, right, down. So you have 6 spots, and you got to pick 3 of them to be right, or 3 of them to be down, whichever one, and the other ones will be the other letter. And if you calculate this, this is 4, choose 2, which is going to be 6. So I'll just write it out carefully. 4 times 3 over 2 times 1 times 6, 5, 4 over 3, 2, 1. These cancel. These cancel here. So this is 2. So it's going to be 6 times 20 is 120. Okay.
Could you explain the purple one more time? Because I'm a little confused if you're like choosing 2 paths, but it takes 4 to get there.
That's right. It takes 4 to get there. So it's like picking, you have to make a 4-letter word with 2 R's and 2 D's. That's kind of like if you have 4 friends, inviting 2 of them to go to the movie with you, because you're essentially picking the 2 spots in your journey to go right, for instance.
Oh, okay. So you're choosing which parts you're gonna. Oh, okay.
Exactly. If you want, you could also think of it as the Mississippi problem, but I prefer to think of it as a combination. Or I mean, the Mississippi problem with 2 letters is a type of combination. Is a combination. And just to confirm this concept, imagine I had another grid that was not a square, but this time it was a 3 by 1, 2, 3 by 4. How many ways would there be to get from one corner to the other, and I can only go right or down? So for example, I can go like this. This is not the most interesting one, but how many ways would there to get from A to B? Nice, Colette. Nice, Dimitri. Very good. Colette, what did you say?
I said 7, choose 3 because I counted the number of different like small lines, and then there were 3 that were going down, but it could also be 7, choose 4, of course.
Exactly. Excellent. So you have right, down, 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 right, right, right. So the number of ways is 7, choose 3. If you want to pick your 3 down spots, or equivalently also 7, choose 4. Either way is good. Dimitri, I really like your question. Dimitri asked, what about in 3 dimensions? So in 3 dimensions, you're going through like a cubic, what we call a cubic lattice. I'll try my best to draw it out here. Yeah, let me just draw it out here. And you actually can solve this using the tools we've learned so far. So if you can only walk along the edges of a cube, and this is not going to work out well, I think, and you can walk through the interior as well. What do you think? How many ways are there to get from a corner here to the other corner in 3D space? It's harder to visualize this, but what do you think? This kind of the previous approach, and let's say you can only move, you're only allowed to move right. I mean, kind of give you an analogous problem that's solvable. You can only move to the right, you can only move forward or up. Right? Those are the only directions you're allowed to do. How would we, if it's a 3x3 cube like this, how could we count the number of paths from one corner to the other? Look very close. It's not 9 choose 3. So I'm going to try my best to kind of draw it out. So maybe I can go red here, then red here, then go here, and then go up. So kind of go like that, like that, like that. So this would be one path, but you can also go through the interior. I didn't cut through the interior at all. So it's 9 choose 3 is a really good try because overall you do need to make 9 steps. And this is actually 6 choose 3 is not bad, not a bad try. Now, I don't know the exact number, but this is exactly like a problem that we have solved before. And it's actually like one in the homework as well. Well, okay, it might be, I might have to be careful here. 9 choose 3 times 3. It might be that. 9 choose 3. So I don't know. So I'll have to be careful about some of these answers. But the idea is, let me ask you this. What formula, and it's not going to necessarily involve combination, what formula counts the number of words you can make like this? Right, 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 F, 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 U, U, U. How many different words are there like that? This is just the Mississippi problem. So it's 9 factorial over 3 factorial, 3 factorial, 3 factorial. This is called not a binomial coefficient, but this is actually called the multinomial coefficient. But this is a nice question. It's a nice connection to the Mississippi problem. Okay, any questions on that? That I'm obviously not going to ask that, but did that make sense? Awesome. Yeah, the idea of converting paths or choices into just letters and then counting words is actually a very powerful and simple idea. Simple but very powerful idea in math. Okay, let's see here. 23. We got 25, and then 29. I like 25. Okay. So for 25, we have let's see here. Yeah, we have to take 5 courses. We have math, science, English, and then other. And for math, there's course 1 and 2. For science, there's bio, chem, and physics. And for English, there's just English. And for other, there's A, B, C, D, and E. Okay, so we have 5 courses are required for admission. And one science course must be selected as well. how many different ways can you select 5 courses on your college application form? So this is a really good problem. If you haven't done it yet, we can watch the solution, but definitely try to do it later. It's a really good problem to make sure you're comfortable with fundamental accounting principle and how to do different cases. So anyone have a good approach, any starting idea what we can do here? So you have to pick 5 courses. Pick 5 courses. You're required to have 1 math, an English, and at least 1 science. And this type of problem, Lily, I like your idea. So walk me through kind of how you were thinking about it. And I'll show you a different idea that I had, but I just want to kind of see how you were thinking about it.
So kind of set up like different spots to put each of the numbers so then you could multiply them in the end.
And why did you say 5 spots?
Because you're picking 5 different courses.
Okay, so yeah, so we're picking 5 courses. Yeah, that could work. I kind of see what you're. I think that would give us a different way of a way of doing it. I'm gonna kind of go about it a slightly different way. But if you got the answer doing it that way, I would like to see kind of how you approach it as well, because there's different ways of thinking about it. But when I see the 4 categories, math, science, English, and other, to me it's already, I feel like, okay, maybe I can organize it as how many ways are there to pick my math course, my science course, my English. So I would put, like you say, I would put four categories. And there's also something a little bit tricky here that this will help with. What do you always have to kind of be mindful of when you see the words at least or at most, and you're doing something with counting? Do you guys remember, did I mention this? Whenever you see the words at least or at most, what should you kind of be in the back of your mind thinking about? Anytime you see these phrases, always think about the term casework or cases. Because there's different situations, and it's going to be hard using the counting principle to account for the different types of patterns that you can get. So if there's at least 1 science course, we might have to do the case where there's 1 science course. Then we can do the case where there's 2 science courses, and then we do 3 science courses. This is math, science, English, and other. Okay, so the first one I'm going to write out in all combinations, and then the next one I'll do. So for math, I can only pick 1 course out of 2, so that's 2 choose 1. Really, there's only 2 options. That's a fancy thing to do, but just kind of show you that every choice you're making, you're picking some group, some small group out of the options in that category. For science, if I want to pick science, what combination do I want to write in for this first option?
3 choose 1 for the first one.
Exactly, 3 choose 1. Nice. And then how about for English? This is kind of a funny one. And obviously you don't need to do a combination either, but I'm just showing you that they're all, like, anytime you're choosing something from a group, it's 1 choose 1. That's right. Obviously, if you're just doing it, it's okay to just leave it as 1. And then how about the last one? We've only picked 1 math, we picked 1 science, 1 English. What about the last one? How many optional courses do we have to pick? we got to pick out of 5. We do 5 choose 2 this time because we need to pick overall 5 courses, and we've only gotten 1, 2, 3 so far. So 5 choose 2. Colette, that's right. Yeah. So this approach is a little bit different. I would have to think carefully how you could do the other approach as well. The other approach you would have to kind of divide. If you say like how many options there are for each like class 1, class 2, class 3, class 4, class 5, or it's also doable. It's the same thing basically, but you just have to divide at the end. Dimitri, that's right. You can choose multiple sciences. So that's going to be the next case. So how many ways are there to pick the 2 sciences? Well, first there's the math course. But now for the science category, how many ways are there to pick my 2 science courses? That's just 3 choose 2. English, always 1 way. But now I have 1 less way to pick my optional. So there's just going to be 5 choose 1. I only have 1 spot, so I got to pick. I have only 5 things to pick. And the last one is, this is English and other. And the last one is math, science, English, and other. I have 2 choose 1, but now there's only 1 way to go with all in on science courses, only 1 English course, and it's 5 choose 0 because I can't pick any of them. So when you multiply this all out, you get 2 times 3, 2 times 3 times 10, which is 60. This one is 2 times 3 times 5, which is 30. And this one here is just 2. So overall, you get 92 ways. Okay. So is it clear how I set it up, why I'm multiplying these different combinations using the counting principle, and each time I'm multiplying like one of these cases, multiplying it all through, I'm thinking about specifically counting the number of ways I can make a schedule that meets this requirement. And these are completed schedules. I've picked out everything I need to pick out for that schedule. But then I can also consider other cases, other schedules that look a little bit different, and I add those numbers because those are kind of like different different completed configurations. What do you guys think? Any questions? Looks good? Awesome. Yeah, any questions? I'm happy to answer if there's any part of it that you... All right, let's try let's do 25. Oh, did I do 24? Oh, I didn't do 24. Oh, no, that's the previous class. I should buy 25. We did 23, 25, 29, 31, 35. Um, 29. So I'll just say something about 31. So in 31, you have these different codons. And a codon can encode some sort of asset, and some of them have multiple ways of doing it. So 31 is just a nice application of these ideas. So 31, you look at that table and it says, how many ways are there to get met, gly, ser, arg, cis, and gly. So how many sort of strings of DNA could produce this protein, which is a chain of amino acids? And by the way, learning these concepts about counting and combinations is really useful if you are interested in bioinformatics and interested in DNA. There's a lot more properties of these that are useful in studying, like what parts of your DNA give you certain proteins. But anyhow, what you just look at here is to say, well, there's only one codon sequence that can give me met. So you can just do one. For gly, there's 4 different codon sequences. So this is number of sequences that give you the amino acid. For ser, there's 1, 2, 3, 4, 5, 6. For arg, there's 1, 2, 3, 4, 5, 6. For cis, there's 2, and for gly, there's 4. So this would be overall, multiply all these numbers, that would give you the number of arrangements of codons, the letters in your DNA, like A, C, G, U, that would give you they would encode for your body to make the same protein, which is pretty impressive. And if you look at the different letters that encode the same amino acid, like usually they're not too far off from each other. Maybe they're switched off by like one letter, and that's makes it pretty stable. So that if something in the DNA is a little bit damaged, your whole body's not going to break down if it's just one piece of it that's off, because it can still make the correct things it needs to do. Okay, so that's 31.
Wait, I have a question about 31.
Yeah.
So we can just multiply across, but doesn't the order of those things matter? Like the met, gly, ser, does it have to be in that order?
It does, yes.
Okay.
Yeah. The met, gly, ser, that's specific to that protein, but the ways to make each of those amino acids, like each of these little pieces, there's one way to make this one, there's 4 ways to make this one, and so forth. But yeah, it's really cool to see this. If you're interested at all in biology, this is a great thing to learn about. A great field to explore. And there's actually one of my friends built a really neat online course for bioinformatics and the math behind DNA. And that involves a lot of this combination stuff. Let me see here. Yeah, 29, I'm going to just skip that one because that one's a little bit involved. Skip that one for now. Then let me see what else. Uh, 31, 35, 34, 35, 34, 35, and 40. Okay, yeah, let's do a little bit of this. And by the way, for 29, for 29 is a little tricky. It says like how many ways are there to arrange 8 books on a bookshelf, so that there's like physics, history, what is it here? Biology, history, programming, are never together. So none of them are touching. And you can apply that idea that we did with the complement, but it's a little bit trickier. It's not that much trickier, but you have to be a little bit more careful, because you can say, okay, I don't want biology and history to be together, but I also don't want all three of them to be together either. So you have to kind of subtract some cases, but then also potentially add some cases in so that you don't over subtract. So if there's some time, we can go over that one, or maybe talk about it next on Tuesday. But yeah, let's do one of these. 3x squared minus 1/2 to the 4th. And it says, which of the following is not in there? Well, it's kind of hard to tell just by looking at it, so maybe we just expand it. So I know that when I expand something to the 4th, I'm going to expect the numbers 1, 4, 6, 4, 1. I can just maybe write down those combinations. This is, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Those are my coefficients. And then I'm just going to be really careful with my parentheses. That's the key here, is being careful with your parentheses and not writing down nonsense. So let's do 3x squared to the 4th plus, and also being careful with the minus sign, 4, which comes from the 4 choose 1, right? This 4 is right here. So that's the coefficient there, times 3x squared cubed times negative 1/2 plus 6 3x squared times negative 1/2 squared plus 4 times 3x squared to the 1st times negative 1/2 cubed, and the last one is plus negative 1/2 to the 4th. Okay, and then we look at these. This is going to be equal to 81 x to the 8th. So that's choice A, we have that. 4 times negative 1/2 is going to be negative 2. So this will be negative 2. And I'm just going to kind of do it. 3x squared cubed is going to be 27x to the 6th. So times the 2 is going to be 54 x to the 6th. Negative 54x to the 6th. Plus 6, and then 3x squared minus 1/2 squared. That's 3x squared is going to be 9x to the 4th times 6 is 9 times 6 is 54. So divide that by by 1/4. So this will be plus 27x to the 4th over 2. And then this next one will be, and you can write them out. I'm just kind of doing it one step. If you're careful, it's better to be careful and actually expand everything and group it together. This will be 4, and then I'm dividing by negative 1/8, so it'll be like 1/2, negative 1/2. So I'm going to change this to a minus sign. It'll be minus 3x squared over 2, and the last one will be plus 1/16. So it looks like the one that we don't have is going to be choice C.
I'm kind of confused where you got like all the numbers, or I don't know how you expanded them.
So let me see here. Did I make some mistakes here? It's very possible I made some mistakes. Lily, isn't 3 times 4? Can you see which ones did you have a question about?
The 54 one.
Yeah, okay. So I got 3x squared, 3x to the third, that's 27, but then, and then a 4 times the negative 1/2 is 2. So 2 times 27 is negative 54. Is, and is that, does that check out? And Kai, okay. Kai, which numbers, which expressions did you have any questions about?
Like, I'm just confused, like, about all of it. Like, don't you have to, like, write out, like, other stuff before you can get to that? Or...
Yeah, well, are you okay? First, are you okay with this, with everything I wrote down here? I didn't do any arithmetic here. I knew these are the coefficients, and then I just plugged it into the expansion pattern. Is this pattern okay?
I was also, where'd you get the coefficients? Because I don't, there's like, I see like 3 and like 1/2, and I don't know where you got like 1, 4, 6, 4, 1 from.
Oh, yeah. Okay, 1, 4, 6, 4, 1. This is really important, right? If you remember, when I wrote x plus y, anything x plus y to the 4th power, the way we thought about it is, it's going to have x to the 4th, and then it's going to have x cubed y1, and then it's going to have x squared y squared. Then it's going to have x to the 1st power, y to the 3rd, and then it's going to have y to the 4th. But the things in front of here are going to be 4 choose 0, because that's the number of ways you can make a word with 0 yeses. And then here's going to be 4 choose 1, 4 choose 2. It's like the number of ways to write down a word with exactly that number of y's. And this is 4 choose 4.
Oh, I see. Okay.
So these numbers 1, 4, 6, 4, 1. It's one of the rows in Pascal's triangle, and it's just the pick, whatever the power is. You just do, like, let's say it's to the nth power, like to the 10th power, whatever it is. Like, let's say to the 7th power. The important coefficients to just keep in the back of your mind are 7 choose 0, 7 choose 1, 7 choose 2, all the way to 7 choose 7. So I just wrote those down to just kind of have them accessible, because if I start writing these combination symbols, it's already pretty messy. So I kind of like to write down the combination symbols on the side, so I can just plug in the number. It makes it a little bit more readable for me. So is that okay? Is that better how I got this formula now?
Yeah.
And it's just, it looks really messy, right? But it's exactly this. I'm just doing substitution. So I'm plugging in 3x squared, but I'm raising it to the 4th power. Then the next step is going to be, there's a 4 out in front, but I'm doing 3x squared to the 3rd power, and then negative 1/2 to the 1st power. And then I step down. The 3x squared is always going to be 1 less exponent, but the negative 1/2 is going to be 1 bigger exponent. And then how do you feel about like the simplifications? Now that you see that, you want to just take a moment, take a look at kind of how I got each of these numbers. It's just being careful with the algebra.
Yeah, simplification looks fine. I was just confused about like how you expanded it.
Yeah, exactly. So that's very good. Yeah, it's just like same as x plus y, but I'm just substituting. And I'm keeping one way to keep it more readable. There's 2 tips here, actually, general tips. First, I recommend writing down the combinations that you'll need on the side, so you just don't have any, like the combination form that has parentheses in it, like big parentheses, and it could really kind of start messing with you a little bit. So just put the numbers on the side. The other thing is there's a minus sign. Whenever you're subtracting and you plug in a minus, the way the formula works is the powers of the things you're adding, or if there's a minus sign, subtracting, the powers are changing. They're increasing one by one, and the other one is decreasing. So if there's a minus sign involved, and you're taking like more and more powers of it, you're gonna switch between an even power and an odd, even powers and odd powers, even power, odd power, and even power of the second thing. So expect to see plus minus in the final answer. Andrew, yes. So just before we move on, any questions on kind of how to do this expansion? And 35 is kind of very similar. Just kind of try to figure out which of them makes sense for that expansion. Yeah, there is a really nice way to do number 28. So I'll just talk about that one as the last one. Oh, and then I want to show you guys just two things, actually. So did anyone come up with a shortcut to do number 28? And by the way, a diagonal, the definition of diagonal, we know what a diagonal of a square is, but a diagonal is of a polygon is any edge or any pair of vertices that you can kind of draw an edge that goes through the inside of the shape. So it's the number of edges you can draw through the inside, but does not touch the boundary of the shape. So rather than just counting it, anyone have a different approach? So the question is, how many diagonals? And there's a really simple approach to do it.
Would it be
Yeah, go
five?
ahead.
Choose some. I know the answer is 5.
But without
we would
kind
start
of
with the 5 points of the pentagon. Sorry.
Yeah, good.
And I don't really know. Would it be? It wouldn't be 5 factorial because 5 factorial wouldn't add up to 5.
Right.
Would it be 3 factorial?
Well,
No.
let's think of the combinations and all these factorials as like our tools we can use to count something. So first figure out what you want to count, and then say, oh yeah, this is 5 choose 2. That's always a good approach, is figuring out like what are the objects you want to count. So anytime you make a diagonal, what are you really picking? Ah, Colette, exactly. Yeah, do you want to share what you said there? That's exactly a good idea.
It reminds me of problem number 14, which is the one where you were deciding how many, or finding out how many handshakes were in the room.
That's right. It's exactly like a diagonal. It's kind of like a handshake between two vertices. You're just picking two people. So this is similar to 5 choose 2. Because if you want to know, like if you have 5 friends, how many handshakes can you make? It's kind of like saying 5 friends, how many ways are there to invite two to go to the movie? Or if you have 5 dots, how many edges can you draw? It's 5 choose 2. But why is 5 choose 2 not the answer? What do we need to do to 5 choose 2 to get the answer? 5 choose 2 is 10, by the way. So if we do 5 choose 2, what are we counting that we shouldn't be counting? That's right. Dimitri, what did you suggest?
Subtract the edges,
Yeah,
the bits that are already red, or that are already black.
Awesome, exactly. So we do 5 choose 2 minus 5. So what's cool is if you can do this for like a decagon, like a really much bigger shape. For a decagon, you guys know how many sides a decagon has?
10.
Yeah, 10 sides. Rather than counting all the diagonals, which will be pretty intense, you could do 10 choose 2 minus 10. And 10 choose 2 is not too bad. That's 45. because 10 times 9 over 2 minus 10 is 35. Okay, before I let you guys go, I do want to mention, and I have this kind of go through this in the notes. There was one question that the other class saw that you guys didn't, which I think is really important. That is number the one with the candies, and some of you might have seen it in office hours. So how many ways are there? How many ways to choose one or more of 5 candies? So in office hours, we had talked that this is 5 choose 1 plus 5 choose 2 plus 5 choose 3 plus 5 choose 4 plus 5 choose 5, which comes out to overall, if you add them all up, 31. But I was curious, somebody in the other class had a really nice idea, which is a really awesome pattern to be aware of. Is there another way to think about this?
I don't really know what I was thinking when I did it, but I got 2 to the power of 5 minus 1.
Yeah, yeah. Can you explain kind of how you came up with it? Or I know you said you didn't know how you think, but what kind of led you to that? That's correct.
I honestly don't know what past me was thinking. I think I really late at night, and I don't remember.
No, it's a really simple idea, and it's awesome because it connects the thing with combination with pin codes. So if you want to pick some of the candies, when you go to each candy, what are you really doing?
It's either a yes or a no.
Exactly. So this is yes or no. So there's 2 options for candy 1 to pick it or not pick it. For candy 2, there's also 2 options. Yes or no, yes or no, no, yes or no, and so forth. So this gives you 32. Why do we need to subtract 1 to get picking 1 or more?
Because you have to choose at least one, I guess, and you can't choose nothing.
Exactly. We want to get rid of the case n, the all no's case. So this brings us to a really nice pattern in Pascal's triangle. And I went over it pretty quickly, and it's simple, but it's not something you maybe immediately would think of, but it's a really nice thing to be aware of. I'm just going to show you where it is here. Where is it? Right here. And I'll post these notes as well. So in general, if you have n elements, the number of subsets you can pick from that n element set is 2 to the n. And this will include the empty set and the original set. So picking none of them is counted, and picking all of them is also a possibility. And in particular, if you look at Pascal's triangle, which consists of those combinations, and you add all the numbers in the row, what you find is you get 1, 2, 4, 8, 16, and then for the next one, you would get 32. I'll just leave you guys with one last idea here. Do you guys notice anything else interesting in Pascal's triangle? What are these numbers? What do they remind you of? Do you recognize them?
Fibonacci? Wait, no.
No, there's some stuff related to Fibonacci was pretty incredible, but something even simpler.
Is it like the choosing?
Yeah. These are the numbers. The numbers themselves come from combinations. But what if I were to write it like this?
For palindromes?
They're all palindromes, but do you recognize these numbers?
Prime?
There's some primes. That's right.
Is it factors of 11?
It's powers of 11, right?
Or
This
powers,
is 1,
yeah.
11, 121, 1331, 1, 4, 6, 4, 1. These are all powers of 11. So my question is, why do powers of 11 show up in Pascal's triangle? And do they always show up? What's going on here? So I'll leave that for you guys to think about over the weekend. It's a neat little pattern, and it's actually connected to an alternative way to understand this pattern using, or to see this pattern algebraically using binomial theorem. And the only hint I'll give you is to explain this pattern and also this one, why powers 11 tend to show up, is you can, inside of the binomial theorem, you can actually plug in for x and y whole numbers. And if you pick the right clever whole numbers, you can get some interesting observations or patterns out of it. So instead of x and y just being symbols, pick some convenient numbers and you'll see something really neat happening. But I really like this observation that you guys made, counting the candies. That's really good. All right, I will see you guys on Tuesday. I will post some practice questions in addition to the homework that we can review. So I think you guys did a pretty good job. Make sure you complete the homework. If you haven't done some of these questions yet, do them on your own before reviewing the notes. That's really, really important. And then try to have the practice questions done by Tuesday so that you feel really comfortable with these concepts. And just message me if you have any questions over the weekend. I'll stick around for a little bit. I told students I would have some office hours, so if you have any other questions, I'll be here for a little while. But otherwise, I will see you on Tuesday.
Mr. Minsky?
Yeah, it's good.
I just had one question about number 28. I just don't quite understand the idea of the when you're talking about subtracting 5 because there's 5 sides.